Okay. The screencast is about intermolecular forces. Okay. IMFs. Okay. Keep in mind that usually these are discussed when we're talking about a pure substance, meaning all of the molecules in the substance are the same. These are generally weaker than covalent or ionic. I would think that they're always weaker. Okay, these are related to the state of matter. Stronger IMFs are going to have a higher boiling point, and that's because you have to have enough kinetic energy to overcome those attractive forces so that those molecules are no longer held together. Okay? There are really three that we talk about: London dispersion, and this is the polarizability of the electron cloud. Okay, so greater number of electrons, these are stronger. Okay, a rod-shaped are going to be greater than a spherical. And it has to do just like the places that your electron cloud can be polarized. Okay, these are also known as instantaneous dipoles. Next one, dipole, dipole. These are between polar molecules. Okay, and it is really the attractive force between that negative pole being attracted to the positive pole. Okay. Remember that all molecules have London dispersion forces. Okay, so they have to be covalently bonded molecules. By definition, a molecule is a covalently bonded substance. Okay, dipole, dipole, these are polar, obviously, molecules. And then you have kind of an extreme case of dipole, dipole, which is hydrogen bonding. And remember, this is between molecules, okay? And it is kind of an extreme dipole-dipole. You have to have the hydrogen directly bonded to either nitrogen, oxygen, or fluorine. These are small, highly electronegative. And what that does with the H bonded, the one electron of hydrogen is really given to the highly electronegative. This leaves this very positive, this very negative. All right, so it's almost like a +1, very, very attractive. All right, so so if something has hydrogen bonding, intermolecular forces, it also has dipole-dipole and London dispersion. Right, and giving you just an idea of how strong the hydrogen bonding can be. If we look at some elements or some compounds really, and say we look at water boiling point compared to H2S compared to H2SE compared to H2TE. You can see I didn't draw it quite right. The boiling point of these does increase due to the number of electrons increasing. Okay, where you would expect, if you were following this trend this way, you would expect water to be here. But it's actually up here, and this is due to that stronger hydrogen bonding, that almost +1. One thing to note is water does expand on freezing. And this it's because of the intermolecular forces forming between those. The molecules can actually get closer together in the liquid form. Okay. Let's talk real quick, giant covalent structures. I'm going to write a bunch of stuff and pause the recording, so we'll be right back. Okay, so let's talk about giant covalent structures. We're going to focus on carbon allotropes. First one we have is diamond. Okay, diamond is a giant covalent. It's going to have the highest melting point. You have every carbon bonded to 4 other carbons forming a tetrahedral. That means it has an sp3 hybridization. There are no delocalized electrons. If you compare that to graphite, graphite again is a giant covalent, but the carbon is bonded to only 3 other carbons, so that's an sp2 hybridization. Layers can slide over each other, and you do have delocalized electrons that move between the layers, so this is conductive. Then the last one you have is the fullerene, which is a C60. You have hexagons and pentagons, carbon rings that forms spheres. Okay, Si and SiO2 or silica. These have a structure similar to diamond. And lastly, we have metallic bonding. I'm going to change colors because I find this really ugly. Okay, so metallic bonding. So metallic bonding is characterized by valence electrons that are delocalized, meaning they're free to move. Often you will hear it described as a sea of mobile electrons. Okay, and those would kind of flow over the inner core positive. Hopefully that gives you an idea. All right, so metals. Hopefully you can see that they would then conduct electricity. Although impurities can hinder the flow due to resistance. And this this structure means that it is malleable. And please get this definition correct. This means you can beat it into shapes without it breaking. Or ductile, you can draw it into a wire. The other thing to note that the melting point decreases as the size of the cation increases. Okay, this is why you decrease going down a group.